Okay, so now the electron leaves the accelerating portion of the cathode ray tube and enters into a set of plates. I'm going to leave a bit of a space here so I have some room to write below. I'm going to put these plates all the way over here. We'll assume that there is nothing affecting that electron between this set of plates, which we call the accelerating voltage plates, and these sets of plates, or this set of plates, the vertically deflecting plates. We will have a voltage difference between these two, as I've described as well. So if I place the negative along the bottom, I would call that 0. And whatever the difference is between the two, I would assign that all to the positive plate. So it doesn't really matter what it is. I'll give it a value, say, of something like this, just so it looks like something we're familiar with. Okay, so now we have this electron moving into this plate just for the simplicity of dealing with the mathematics. We're going to make it so this electron enters right in the middle of these two plates. So this electron entering into the middle here has a path of no deflection straight through the center. If this has a voltage difference, then I can, in this case, because it's positive above, I can affect the path of that electron. This electron will be getting pulled towards the upper plate as it passes through. It will be pulled towards that upper plate in a parabolic motion, just as a ball falling out of the sky is accelerated towards the ground, or if I threw a football horizontally, I have that same form of acceleration. It might be easier to see that comparison if I made it positive on the bottom and negative on the top. I'd see that parabolic motion of the electron downwards. So the electron is deflected by these plates. And again, if I made them the same, so there's no potential difference, that electron will go right through, and I can vary this by having some dial on the side which affects what the voltage difference is here. And I could even switch the polarity here, making this the anode and that the cathode. That is, making this the positively charged plate and that the negatively charged plate, and cause my electron to flow downwards. So we have what we can see as kinematics. We have one dimension being affected by an accelerating force, and we have the perpendicular dimension having no force affecting it. So we end up being able to address this component of the CRT with kinematics. So we state our horizontal and vertical. We've got our initial velocities, final velocity, our acceleration, distance, and time. And all of these values are referring to this component right here of the CRT. So the initial velocity in the horizontal is the velocity that it attained when being accelerated through these plates right here. So that velocity is VFA. We have the final velocity being the same because there's no acceleration. Now we're going to be looking for dependencies that each of these variables have on what's going on between these two plates. Now, just speaking of this before we get into equations, the acceleration here is going to be dependent on the force that this charge incurs as it moves between these two plates. The deflection will be dependent also on that voltage and the force that the charge incurs as while moving through those two plates. The final velocity and the y will be dependent on that voltage, or the force that is acting on the charge as it moves between those two plates. So we're going to go around and find some substitutions to make. And in problems that you're given, any one of those substitutions may be up for grabs. If you understand where they came from, those substitutions will be easier for you to make. So let's now make some substitutions. I'm going to begin with the acceleration, y. The acceleration is equal to force divided by the mass. There's only one force acting on the electron as it passes between these two plates, and it is due to that potential difference there. So this is an electric force. That electric force is dependent on the field between those two plates. Fe is equal to Q, that is the charge that's moving between the two plates, in this case an electron, times the electric field. And this electric field is dependent on that voltage. If that voltage difference is larger, E will be larger. If the distance is greater, then E will end up being smaller. So E, the E field, is even or uniform everywhere between these two plates. So if we want to know what E is, we take the potential difference and we divide it by the distance over which that potential difference takes place. That equals our E field. So we can make this substitution in here for Fe. And further, we could make that substitution for a new value now, or a new expression for the electric force, back in for Ay. So for Ay, we are going to have Fe, which is now Q, times E, here's my E, and this distance I should be labeling on my diagram so it's clear what I'm talking about. I'm talking about the distance between the bottom plate and the top plate. So here's my E. Q times E is Fe, and now I divide by M, or equivalently multiply by 1 over M. The expression written in a more simple fashion is Q, change in voltage, or voltage drop, mass times the distance. Where this voltage drop is a deflecting voltage. It causes a deflection of the electron off its original path, which is straight, and we refer to it as the deflecting voltage. Now we're going to have a look at dyP, the deflection that this electron can go through. So instead of talking about what are the possibilities, we're simply going to head and do kinematics about that. The deflection in the y is going to be equal to V naught in the y times t plus 1/2 ay times t squared. The initial velocity is 0 because it enters the deflecting plates horizontally. So we get the following. Ayt squared. If I wanted to, which I will, I would like to substitute in this new expression I have for A now. Since A is dependent on these values, which are measurable values or given values, I will take that and I'll plug it in here for the A. So I have Q, change in voltage, over mass times distance times t squared. Now, as is the case with calculus, if we would like to determine this deflection, we must find out all the variables it's dependent upon. Now, excuse me. Now, the time is dependent upon how long the electron is between these two plates. And that value is obviously dependent on how quickly the electron's going when it enters those plates. This value is right here. So now we find out the time further is dependent upon how quickly we accelerate the electron. Now, just having said what we've said right there, we can intuitively we know we can determine or talk about the effects of this deflection by realizing it is directly related to the deflecting voltage. That means that as this voltage here goes up, increases, that deflection will increase because the force will be larger and we'll be causing more of an acceleration in that direction, as indicated by this equation right here. We can also intuitively conclude that dy is proportional to the inverse of the accelerating voltage, meaning that as the accelerating voltage increases, dy goes down. And using our intuition in our reasoning, we can say, well, this deflection here is dependent on how long this force has to act. If I decrease the amount of time the force has to act, the deflection will be smaller. Well, decreasing the amount of time the force has to act is equivalent to decreasing the amount of time it takes for this electron to get from the beginning here to the end. Well, that time is dependent on how fast the electron is traveling. And how fast the electron is traveling is dependent on how fast it's going coming out of here. How fast it's going coming out of here is dependent on what this accelerating voltage is. The higher that voltage, the faster it will be going, and we can see that relationship right here. A direct relationship between velocity and acceleration. So intuitively, we can conclude that this deflection is proportional to the deflecting voltage divided by the accelerating voltage. This is not an equation, this is a proportion. It simply tells me the relationship that if I double my deflecting voltage, that deflection will be doubled. If I double this, that will end up being halved. If I double this one and double that one, nothing will happen to the original deflection.